This is a very brief video talking about the limitations of the chi-squared test. This is a very important video, and that is why it's being set aside on its own and not being tucked in with any of the other videos talking about the chi-squared tests themselves. So, we have looked at both chi-squared tests for independence and chi-squared tests for goodness of fit. We've seen that, for example, we might get a chi-squared test statistic by looking at the sum over all of the categories, and those might be the categories in a contingency table or the categories of one variable, one categorical response variable. And it's based on the difference of what we observe minus what we expect squared over what we would expect. And so what we expect might be based on the assumption of independence or the assumption based on the null hypothesis of a specific model. And so once we get our chi-squared test statistic, we then get our p-value based on the assumption if the null hypothesis is true. We plot our chi-squared observed, and our p-value is everything that is more extreme. But here are some things to note. The degrees of freedom is not based on sample size. So that's the first thing. This is the first time we've dealt with degrees of freedom that have never had anything to do with sample size. So whenever we did a t-test, whenever we did an f-test, whenever we've had anything to do with any distribution that had degrees of freedom before, the sample size always came in some way. The chi-square test does not. It only has to do with the test that we've dealt with the number of categories. So that might be the number of rows and columns in our contingency table or the number of categories for one sample z-test, or one sample, one categorical response variable. So that's one thing to be mindful of. So let's think about this then, and we will see an example in another video how this can be really important. So all the chi-squared then is doing is looking at how different what we observe is from what we expect, and then it's scaled by how big our expected value is. So when we get a small p-value, such as in the previous example, a small p-value, as we have seen, is strong evidence against the null hypothesis. This is true, and it's the same as we've always done. So if we're doing a test for independence, it is strong evidence for association, because the alternative hypothesis would be association. However, it does not tell us that it means we have a strong association. So a small p-value does not mean strong evidence, does not mean a strong association. So strong evidence is not the same thing as strong association. We have seen this in previous work when we were talking about regression. So we could get small p-values in regression and still have a pretty small slope, right? And that would be kind of like a weak effect, right? So we would have a big increase in x and maybe a small change in y. The same thing is true here. We can get a change in our categorical explanatory variable and still have maybe only a small change in our proportion. So that would be a pretty small association, a weak association. So a small p-value just means that we have strong evidence of an effect, strong evidence that a change is occurring. But it doesn't necessarily tell us how big the change in our proportions in this case are. It also doesn't tell us the direction. Remember, the chi-squared is based on squared values, so we can't do a two-tailed test. So if there is a change In the proportion, when we go from one category of the explanatory variable to another, it just means, okay, we have evidence that a change is occurring, but we don't know the direction of the change. And again, we don't know how big that change is. And another huge caveat, and this is something to bear in mind for all hypothesis tests, not just these, small p-values do not prove association. We have never proven anything in this class or any others, so we can't prove anything with statistics. A small p-value just means that for this particular sample, we have, by chance, with all that uncertainty that comes with sampling, observed something that is compatible with an effect. Another sample would give us an entirely different p-value. It might still be a small p-value with that other sample, but we still haven't proven anything. We just have evidence based on the design of the study and the sample that we have of an association or of an effect. It does not mean that an effect actually exists, and it certainly doesn't mean that the effect that we observed is the effect that exists. So we don't prove anything. On the contrary, on the flip side of that, so the converse of this, a large p-value doesn't prove independence, right? So if we happen to have a sample where there are small differences because of everything we just talked about, right? It could just be that we have one of those unusual samples. We never prove anything. So we don't prove association does exist, but we also can't prove independence. Because we're based everything on the assumption of independence, we can't prove that it does exist. Right? All we can do is say, well, our data are not compatible with an association, right? The defendant is not guilty. We can't find the defendant innocent because we've predicated everything on that assumption. So if we get a p-value of 0.999, we haven't proven that there's independence. We just have data that are highly compatible with independence. But there are a lot of other models, a lot of other options that our data are also compatible with. In addition to independence. So we can't make that step. We cannot go that extra step farther. So we have to think about all those other what ifs that are out there. So think about all those other null hypotheses that are similar but not exactly the same as ours that would also give those high p-values that would also do a good job of explaining our data. All right, so those are the caveats, those are the limitations of the chi-squared test, and they're not really unique to the chi-squared test, but but because of the nature of the language that we use, they're really common pitfalls for the chi-squared test, particularly the chi-squared test for independence and the goodness of fit. So we never prove anything. We can't accept the null hypothesis, for example, that our model fits well, that our model is the right one. So don't fall into that trap.